will start very by elementary questions, just going back to an ODE. In some sense. So this is a little bit an outline of my talk. So I will try to explain things on really on a very easy framework. So the finite dimensional framework, and then I will move a little bit to more complicated situations. Okay, let's start with the Hamiltonian system and finite dimensions. So you take a phase space that is R to N. You take a Hamiltonian that just, for example, a C1 function. You consider as skew-symmetric matrices, and you can then define a Hamiltonian dynamic system just by taking the vector field. So you define the vector field, just the gradient of the Hamiltonian functions, then you apply the skew-symmetric matrices. I will switch sometimes from representation with real variables. Sometimes I use real variables, sometimes I would use complex variables, but this is totally analog. Okay. Once you have defined your vector field, then you just look to the ODE that is defined by the following expression. So the derivatives of u of t is just given by the action of the vector fields on u of t. This is classical, almost on baby school, we learn this. So this is an ODEs where the vector fields comes from Hamiltonian functions. And the main issue one can ask is whether we can solve this type of equations whenever we specify an initial condition. So you fix an initial condition, you try to solve the equations in the sense that do they exist solutions for these equations? Do we have global solutions? Do we have uniqueness of these solutions and so on? Cauchy-Lifshitz theorem is among the main results here. Yeah. Also, the Peano theorem is among the main results. Peano theorem tells us that since the Hamiltonian is C1, so the gradient is C0 function. So by the Peano theorem, there exists local solutions for each data. But we may lack uniqueness for solutions, even on these situations. That's a standard. There is a lot of ODEs that shares these properties. And one of the main questions that I'm interested on is the completeness of the vector field. What it means completeness here is that for each data, each initial data, there exist global solutions for the each or for the Hamiltonian systems. I anticipate this is really a very easy framework, and this is really very well standard and well understood. The purpose here is to try to found a sort of generalizations of this type of results, of existence of global solutions, whenever you have a sort of additional ingredient, which is probability measures on the phase space that have some properties. This probability measure is either invariant formally by the equation, principally the Gibbs measures, or it has itself solutions global on time and so on. So anyway, let's start step by step. And let me recall what it is, a sort of Gibbs measures. So with the same framework, so what I will call Gibbs measures, if this type of integral, so you take the h is the Hamiltonian function, whenever this integral is finite, then you can define the Gibbs measures to be just the Borel probability measures defined by this way. So it's the Lebesgue measures on the phase space multiplied by the exponential minus beta of the Hamiltonian. And beta here is just introduced to keep relation with statistical physics and to see that it is something like 1 over the temperatures. But we can just take beta equal 1 everywhere on the slides. So this is exactly what it is, Gibbs measures. And classical results tells us that if you consider the last Hamiltonian vector field, and if you suppose that either, for example, H is sufficiently regular, we are able to prove that there is a complete vector field, then the UV theorem tells you that the Gibbs measure for sure is an invariant measure for the Hamiltonian. What does it mean exactly? So the global Hamiltonian flow of the equation preserves the measures. So this is the image measure or the push forward measures of mu beta, the Gibbs measures through the flow of the Hamiltonian systems. More precise way. So if you take any Borel set, you just take the inverse image of this Borel set, and then its measures with through beta is the same, the one with okay, so so that means any Gibbs measures, whenever we are able to define Gibbs measures are invariant by the flow. This is very good, but that also puts somehow sort of questions. So in order to see that a measure is invariant, we need to construct the flow first. But it is maybe possible to define a notion of invariance that is weaker than the statement that allows to see what it means a measure that is invariant with respect to vector field or to the dPs, and to construct the flow thanks to this invariance. Okay, will be a little bit the philosophy what we are doing. Okay, so one of the points that I will a little bit comment on it, that the Gibbs measures are of course invariant measures, but they are more than invariant measures. They reflect a little bit sort of statistical equilibriums of the system. So this is in relation with statistical mechanics. So either you are, there are many ways to define these properties. One of the popular way is to introduce entropies and to see that the Gibbs measures are minimizers of this type of entropies. Another typical property that is also very much known on quantum statistical mechanics is what we call the Kubo-Martin-Schwinger condition. This originates mainly on quantum mechanics, and it characterizes equilibrium states for quantum systems, but it have a counterpart for classical systems. So it can also be used to characterize equilibrium states or equilibrium probability measures on these situations. Okay, let's look a little bit to now. Once we have understood what it means, Gaussian measures on finite dimensional Hilbert space, we would like to extend it to systems with infinite degrees of freedom. And in particular, we would like to define what it is that Gibbs measures on a Hilbert space with infinite dimension. Okay, we need a little bit of setting. Hopefully, it's not too much complicated. So you fix a Hilbert space that is separable. You take a positive operators, that is unbounded operators, that goes from a domain, its domain H, and you assume that A is a positive operators. That means this equation here. So from these operators, we do have actually a linear Hamiltonian dynamical systems that is given by these energies. This is the energy of the Hamiltonian system. And once you have the energy, you have also the vector field that looks like this. And now I'm using the complex variables instead of real variables. Otherwise, we have to put the J. J is equivalent to minus E the complex. And you get a linear field equation that is given by the derivatives with respect to time of ut is actually equal to the vector field applied to ut. So exactly the same framework as the finite dimensions. Okay. Now, let's assume more assumptions in order to be able to construct Gaussian measures first, and then to perturb the Gaussian measures and obtain Gibbs measures as a perturbations of Gaussian measures. So one of the easy framework to construct Gaussian measures in infinite dimension is to use these assumptions on the operator A. We're going to assume that the operator have a compact resolvent. Then you can use the spectral decompositions of the operators on this way, and you do have orthonormal basis, AJ, and the lambda J is the eigenvalues of the operators N. And this assumption will play a key role. So we will assume that there exists real, positive real, so that you do have something of this type. So that this you have a summability conditions on the eigenvalues. This is will guarantee the existence of Gaussian measures in some larger space than H. Okay. Unfortunately, the Gaussian measure in finite dimension is defined, of course, for the phase space, these finite dimensions. But in infinite dimensions, your Gaussian measure is usually extended to a larger space. And this S will allows us to define what is the proper the the right space to consider to define the Gaussian measures. So it looks like weighted Sobolev spaces. So you just define a new scalar product through the operators A. This is what gives you for any power R, gives you a Hilbert space HR is positive. And then I look at H minus S. So this is negative Sobolev spaces. And these are positive Sobolev spaces. And the S is the S on the previous slide. So it's connected to the summabilities of the inverse eigenvalues of the operators. And so you have a Hilbert ragging. So this is H, this is HS, and this is H minus S. And if you are on a similar framework, this is, you can think about like L2 space. This is a positive Sobolev space, and this is a negative Sobolev space. Typically, this is what we have. Okay, so once we have this, now we are able maybe to define again what it is, a free Gibbs measure or a Gaussian measure. Gonna be formally looks like this, but this is has no meaning because we don't have the big measure dimensions. But formally, we can at least we can define through results that are known a long time ago. But let me at least recall the exact definitions of Gaussian measures, what it means. So Gaussian measures in finite dimensions characterized by two ingredients, the B and the covariance. Once you know the B and the covariance, you know the your measures, the Gaussian measure. In infinite dimensions, what we mean by Gaussian measures is that maybe it looks like a little bit complicated, but you should think it's probability measures on the negative Sobolev space. Probability measures have the total mass on the negative Sobolev space. But what defines what defines the big Gaussian is that on any linear continuous form is a Gaussian random variable. All the directions are gives you actually Gaussian random variables, and this is what defines you the covariance and defines also the mean. So once you know the mean and the covariance, you know also the Gaussian. Classical result on this field tells you that this is theorem about Gaussian measures. Suppose that you assume the condition about the small s that is related to the inverse, the summability of inverse eigenvalues. Then there exists a unique centered Gaussian measures on these negative Sobolev spaces. I'm going to call them all the time mu beta 0. So mu beta 0 going to refer all the time to the Gaussian measures. And mu beta will be the Gibbs measures. So it's perturbations of the Gaussian measure. And you can characterize it again by it's centered one. So so the M on the previous slide is equal to 0, and the covariance operators can be defined to be this one. Okay. So there are different. Indeed. So this formula, what we are saying here is exactly that what hides the fact that trace of A inverse minus 1 plus S is finite. So it's a condition on the trace space. This is very well known on Gaussian measures. So somehow, whenever you want to define Gaussian measures, you need a sort of conditions of type trace space. Okay. Now we have the setting on infinite dimensions. So we have the linear operators. We would like to perturb these linear operators by a nonlinear function or linear operators in some sense, and study the existence and uniqueness and things of this. Well, we will study only one question. Okay, so now let's move to nonlinear Hamiltonian systems. How to build nonlinear Hamiltonian systems? We start from the linear one. with the compactness condition and the one about the eigenvalues. So you take any nonlinear functional that define it on the negative subulus space, taking real values, and you, in principle, I'm going to assume two conditions. In practice, this covers a lot of equations. Let's show you later that most of the equations that I'm interested on are already included on these conditions. So you would like, so the main idea actually, you would like now to, so you have defined the Gaussian measures and you want to perturb these Gaussian measures to define the Gibbs measures. One of the ingredients in the finite dimension is that this guy is integrable with respect to the Gaussian. So if P equal 1, then this is exactly the minimum thing that you need to define the Gibbs measures. I will assume for P because all the examples that I know, it works for all. But you can take P equal 1 or P equal 0. There is another assumption that I will try to explain. This is unfortunately, is needed in infinite dimension because we need a sort of a differential calculus. And once we would like to define a good differential calculus in infinite dimensions, and it turns that the Malievin calculus is the right thing to use in order to. And this is the sort of, I will explain it later, okay? Let's focus a little bit on the Hamiltonian function on infinite dimension. So this is the free energies, but I should not use the statistical mechanics. Okay, so this is the linear energy or the imperturbed energies. And this one is the non-linear one. So divided on two parts, H0, He. And the vector field is just the differentiation with this of these linear functions with respect to U bar. Okay, so it gives you minus the complex number, okay, and the AU, and then you get the gradient of HE. Okay. Then then there is a natural question. What is exactly the gradient of HE? Since HE is not totally smooth, so doesn't make maybe sense. That's why we need the Malievin calculus to define this model. Once we have this in mind, so we can then set up. So you have the field equation. You can write the field equation. This is classical argument. Either you write your field equation on the interaction representation or you write it on the original representations, and both are equivalent in some sense. We'll prefer to write it on the interaction representation, so you will be only writing these quantities. So it becomes now a time-dependent vector field instead of time-independent on the beginning. Similar. So this one, so keep in mind that this one is just minus E gradient of HE. And this is the evolution with the linear operators, and this is the inverse evolutions. And this is. Yes. Yeah. These ones are very nice because the spectral decomposition and that they are in the, so they preserve all the negative and positive subunit spaces. They don't give. To define the equation, you don't really need to list trace class. The main purpose of the trace condition is about the construction of the Gaussian measures. And so you needed to construct the Gibbs measures. But if you are not don't need Gibbs measures, just formulate this one and it's fine. Okay. Let me little bit explain what is this in particular. What is this this gross Sobolev space, and what is in elementary way? What is this Malievin gradient? Since you are in infinite dimension, one argument that is very effective is just to consider functions that depends only on finite number of variables. And these type of functions if you consider them smooth, then there is you do have a very good differential basis. No ambiguity on this level. Okay, so you define what we call cylindrical smooth functions by just projecting down on a finite number of modes or directions, and you said that all functions of this type, with phi being smooth, is cylindrical functions. And on these functions, you can define without ambiguity the gradient of f, and it makes sense, and it is also smooth again. Okay. Um, Now, what is the Baliavin derivatives, or what is the gradient of the nonlinear functionals, is defined by functional analysis. You just define the operator gradient on the smooth cylindrical functions. This is makes sense, and this is the linear operator. It's easy to see. And then you just study whether these operators could be closable operators or not. So then you define a sort of natural domain of this gradient, and you're gonna consider all the nonlinear functions that are on the domain of these natural operators. So Maliavin derivatives is the closure of such linear operators. And once you have defined the gradient, you also define naturally the gross Sobolev spaces in the same spirit like Sobolev spaces finite dimensions as well. So you just assume that what is a function that is on the gross Sobolev space, D1P, with respect to the Gaussian measure, is just a function that is on the LP space with respect to the Gaussian measures, which is on LP, and also its gradient is also on LP. Of course, the gradient goes to H minus S. So not a real valued functions, instead is vector valued functions. So once you have these quantities finite, then these functions belongs to the gross Sobolev spaces. And it will play a key role. Okay, now we understand what it means, the differentiation for these equations. We understand what is the gross Sobolev spaces, and we have the full setting for this problem. So we can proceed a little bit more. So what is now Gibbs measures for us, an infinite dimension? I just recall a little bit the setting. So the linear operators with the compactness condition, with the compaction on, or with the condition on S and the eigenvalues. So you take something that is integrable with respect to the Gaussians, and where HE is differentiable with respect to the Maliavin calculus. So now we understand what, and you have the vector fluxes. Now the Gibbs measures for the dynamical system that we just described is just these probability measures. So the Gaussian measure multiplied by this weight and normalize it naturally by what we need. We have probability measures. Then there is a question. Okay, can we check whether these Gibbs measures are invariant by the Hamiltonian flow? Then we do have a sort of duality. Either we are able to construct first the Hamiltonian flow, then we check that this Hamiltonian flow leaves invariant these Gibbs measures, or the opposite, then we already have constructed the Gibbs measures, use the Gibbs measures as a tool to construct the flow. Okay, which seems maybe unnatural, but in these questions, this setting is going to be very natural. Okay. Now let's move a little bit to the KMS condition and to statistical properties of these Gibbs measures. In particular, I mentioned this entropy condition and the possibility either to describe it through entropy conditions or through these Kubo-Martin-Schwinger conditions. Entropy, so for entropy, you just you define the relative entropies on that way. This is the standard way to define it. Of course, we are in infinite dimension, but doesn't really matter. It's similar to the finite dimensions. Doesn't really matter. So you just define that this quantity is the relative entropy, and then the Gibbs measures mu beta is the unique minimizer of the free energy functionals, which is given by this quantity. So this is the relative entropy, and this part is keeping track of the nonlinear part, H. So that you get really the full Hamiltonian, and then it's unique minimizer of this. Okay. Now, this is one description of, or one characterizations of equilibriums through entropies. Another interesting approach is to use the KMS condition. However, the KMS condition uses a little bit. So in order to define what it is a KMS properties or KMS condition, you need to introduce further ingredient of the setting. In particular, you need the Poisson structure. So this space that you work on needs a little bit of Poisson structure, but Poisson structure Hamiltonian system. You have natural Poisson structures on them. So again, so you take these cylindrical smooth functions, and remember that you can define on finite number of directions, then you take on R2n. This you take phi on depending only on 2n variables and the other one on 2m variables. And then you can define naturally the Poisson brackets because they are smooth functions. You can differentiate them without any problem. And then you can define naturally the Poisson brackets in the similar way as on finite functions. One of them does not depend on the variable. Okay, good. Now we have all the agreement to define what is Kubo-Martin-Schwinger condition. And for a bit maybe historical point of view, it was at least done by Galavotti and Barbouven. Also Hagen discussed this and probably many other people before. I think it is the 70s. The 70s. And that these properties was discussed between the 70s and until the 80s. And then forgotten totally. Unfortunately, people developed much more. Okay, so what is probability measures on the setting we do have? It is a classical KMS state or satisfies the KMS conditions if you want at the inverse temperature beta if it satisfies these conditions. So for any test functions, f and j looks like test functions. Any f, okay? So the integral with respect to the Poisson bracket f and j with respect to this probability measure should be equal to the gradient of f applied to the vector field related to the dynamical systems, and then you multiply it by j and integrate with respect to. So it looks like a dynamical version of the characterizations of equilibrium states. Okay, and let me recall that the Hamiltonian looks like this, and the vector fields looks like this. So it depends on the vector fields and depends also on the inverse temperature. You change the inverse temperature, you change also the measure.
Could you explain the relation to the quantum KMS condition? So why this a classical KMS condition? Because it's quite different, right? You extend analytically,
Yes.
and when you go to from one strip, in one strip have X, Y, and then
Yes.
commutes. So why is this a KMS condition?
Takes another talk.
Sorry?
To need another talk.
Oh, I see.
But there is a close connection between them, and then we are able, in some sense, to link the quantum KMS condition to the classical KMS condition through a semi-classical analysis.
I see.
So if
Yeah.
you do a semi-classical analysis, then you really can see that the quantum KMS condition that is written by an complex analytic extension of the dynamic and so on
Right.
is really equivalent, leads to this.
I see. It's
So it's
interesting. Yeah.
possible.
Mm.
Okay, but formally they don't look like the same. Formally they don't look like the same.
No,
Quite
you can read
different.
it different.
But maybe just a hint is that this is should be interpreted as the commutator. So Poisson bracket or Poisson structures is the equivalent of commutator. So this is, and the mu is just the state applied on a certain commutator gives you something like that related to the Hamilton. Okay. Let's now come to the problem. So I said that for the entropy is enough to entropy is enough tool to characterize the Gibbs measures. How about KMS condition? Is it really able to characterize Gibbs measures or not? And then this is was our question with Badran. So we set a sort of KMS principle that allows to see that whenever you have a probability measures, that is absolutely continuous with respect to the Gaussian measures, and so that it's such that its radon-Nicodim derivatives is on the Gross-Malievin or Gross-Sobolev space 1, 2, then mu is a classical Kermes state of the Hamiltonian if and only if it's a Gibbs measure. So under some assumptions further of regularities, so any probability measure that satisfies the KMS condition is for sure a Gibbs measure, and the opposite is also. So this gives us a sort of KMS principle in some sense. So in the favorable case where we do have only one unique equilibrium candidate, it is really characterized by the KMS condition. This is what we expect. Okay. Very good. So so far, now I will switch a little bit. So we have understood that, maybe summarize a little bit, that we have understood what it is, a Gibbs measures, finite and infinite dimensions. We have understood also their statistical properties. They are invariant by the Hamiltonians, if we are able to define the Hamiltonians. And they have also further properties that are statistical properties of equilibriums, and we are explaining this. Okay, now the another contribution that I would like to explain is that it turns that since it's easy to define the Gibbs measures, and that the Gibbs measures is sort of invariant measures. So if you take J is equal to the constant function, the Poisson bracket of a function with another constant function is 0. So this gives you 0. Then it gives you that the integral of gradient fx with respect to the mu is 0. And this is exactly the invariant measures without defining any flow a priori. So you can define a concept of invariant measures without defining the flow flux. And we're going to see that whenever I take an invariant measure, then I will be able to build a global solution from this. This is one which is coming in the next part. Okay, let me introduce a little bit. Now we move a little bit to maybe a little bit larger setting, which is the following. So if you take a separable dual Banach space, what it means that you take a Banach space E, and then you take its dual. So that means B is a dual of a Banach space, and it is separable. Then we raise the following question. Consider, take any vector field, not necessarily time independent. Could be, for example, time dependent, and it is not necessarily continuous, neither Lifshitz. Okay, so all the techniques possible of building solutions are not available in some sense. So if you take a vector field that is Borel vector field, so it's measurable, you would like to solve these equations gamma point t is equal to vt gamma t with a condition x on b. So you would like to do this, and one of your ingredient is that you do have a measure connected to this problem that is solution of the problems of the Liouville equations for all times. I will try to explain. So maybe let me stay here for the. So our main purpose is to prove that the almost sure existence of global solution to these initial value problems. So similar to Payano theorem, but you need, since it's almost sure, so you need something, you need a measure. So these measures is the following. So we're going to use a stationary probability measure satisfying statistical Liouville equations and some integrability assumptions on the vector. So let me explain this in more details, more carefully. So so we'll say that a curve of measures mu t is narrowly continuous with respect to time, if just it is continuous with respect to the with respect to the weak topologies for measurement. So whenever you take a function that is bounded and continuous from B to R, this function is continuous on time. Scalar continuous on time. So this is in our topologies. So now, what is a statistical Liouville solution of the problem is any narrowly continuous curve that satisfies these equations. that is a bit similar to what we are doing before, quite similar to the equation that appeared before. So you differentiate this in terms of distributions. And distribution, this is only the one-dimensional thing that depends on time. So you differentiate this, and you ask that this is equal to this one. Okay, if this is true for all cylindrical smooth functions. Okay, so this is, will be the key ingredient for us, is that there exists global on time measure mu t that satisfies these equations, which it turns on practice, for example, on examples, it's easy to solve these equations. Very, very much easy. Okay? So please ask questions if it's not clear. So now we come back to completeness. So then I explain our second result with Shahnaz and Badran. So let me recall a little bit the setting. So you take a separable Banach space, or a separable dual space. You take a Borel vector field. You assume that there exists mu t. T is a solution for all times. It's not a local solution. This is really the key ingredient in some sense. So since this guy is global on time solution of the Liouville equation, then, and you assume these conditions of integrability that I talked about. So the integral with respect to mu t of the vector field that is time dependent is locally integrable on time. Just the integrability is on time. And mu t satisfy the statistical Liouville equations that I showed before. Maybe I can go a little bit back. So this is the Liouville equation. Okay. So we are just assuming that the existence of global solutions of this guy. This global solution could be, of course, a stationary solution. If it is a stationary solution, then this is drops at zero, and you have this. So any solution will do in some sense. Will be test. Then the conclusion is that then there exists a measurable subset of total measure equal 1, so that for any x on initial data on this set, there exists global mild solutions to the initial value points. Somehow looks like a Peano theorem without continuity of the vector field. But we replace the continuity of the vector field with the fact that there exists a measure, natural measures that satisfying the Liouville equation and satisfying these conditions. Okay. Still have time? 8 minutes. Okay, so this is a maybe very abstract theorem. We should maybe put some examples on. I will not discuss a little bit the case. You can ask questions. So first of all, there is an example that shows that if this conditions breaks down, so you can take a vector field that's satisfying the Liouville equation without satisfying this, then you can construct situations where you don't have global solutions. So this shows that sort of this condition is somehow optimal in some sense, thanks to this counterexample. The counterexample happens for vector fields that are C infinities. So it's not a problem of smoothness. It's a matter of integrability rather than smoothness. So this is an example that we took from Annabella Cruzeiro. And it turns that it shows you that this satisfies the Liouville equation, and the initial condition, the initial value problem is equivalent essentially to this thing, this ODEs. This ODEs is that you don't have the global solutions for any data matches except 0. The solution that is really global is 0. All the other solutions are not 0. Okay, so you can apply it on ODEs, but you can also apply it, of course, on PDEs. So on PDEs, the main applications are NLS equation. I will give one of the examples. So you take the torus, either on dimension 1 and 2. You write the nonlinear equation. We have seen this maybe on the talk of Zhao. discussed a lot about there is a zoo of equations actually, by the way, studied. So there is a lot of equations, but here the framework is that we are in the torus, not on the full space. We are on the torus, and this is Laplacian here, and you consider the equation to be in negative Sobolev spaces. What means a little bit compared to yesterday to the talk of that is that it's supercritical equations. So you are not able to apply the techniques that we know that gives you global solutions or even local solutions by the standard techniques. So it's a supercritical, it's not subcritical, neither critical. So you are in a regime where you're even not able to make the machinery of three-card estimates, fixed point arguments, profile arguments, and so on does not work. Okay, so the only way probably is a probabilistic to build global solutions. So the Hamiltonian looks like this, natural thing. It's a cubic equation and a cubic analysis equations. You define this on dimension one. However, on dimension two, you need to build a little bit a sort of renormalizations of these cubic nonlinearities by some argument to just cut for a finite number of modes, and then you subtract self-energy, and then you take and you build something that is on the right spaces. So this is well defined, and is on the LP spaces. You can see that this guy is actually exponential minus beta HE is on all the LP. This is enough to define the Gibbs measures, and this is enough to define the Maliavin calculus and to use it. Okay, then maybe recall a little bit. So if you take X to be one of these, so J here is one of these cases. Huh? J is either on dimension one or on dimension. Both cases work. And for this, you do have this. And then suppose, even more generally, if you suppose that you have this framework with a J that belongs to these things, assumptions, satisfying these assumptions, then you can check this small argument that the Liouville equation holds true with this choice of mu t. So this is what I said, that constructing global solutions for the Liouville equations turns to be very easy. And this proposition shows you how to build the global solutions. It's just the Gibbs measures evolved with the free dynamics. This gives you very easy global solutions for that. Once you have the global solutions and the integrability condition, you get automatically with our theorem existence of global solutions are more sure. But you may lack uniqueness, of course. It's like Peano theorem. Okay. So that's what we summarize a little bit. Maybe it's time to stop here. And so one of the applications is like what I said, is the NLS equation. And you can do it on this way. And you can check that you do have global solutions for the Liouville and the integrability condition holds. Then you get the result. This is what I'm saying here, this theorem. And you can also apply these general theorems to a lot of other nonlinear PDEs. I'm going to give it a list. So it's not necessary to be Hamiltonian, by the way. So I focus a little bit for Hamiltonians because it's easy to introduce them and they have more appealing substance to talk about. But it's not necessary. It works also for the Euler equation. It works for the MSQJ equation. This, people familiar with fluid mechanics likes very much this type of equation. It's a sort of interpolation between the SQJ equation and between the Euler equation. It works also for the wave Clay-Gordon equation, Hartree equations, and so on. The nonlinearity is not necessary to be right? It could be on any gross Sobolev space. You can sum power whatever you want. Okay. And something that I did not totally explain is that maybe it was also on the talk of Zhao, is that for nonlinear analysis, it makes this importance that the system is focusing or defocusing. This is very important. And the example that I'm citing here, at least for dispersive nonlinear PDEs, is these parts are defocusing ones. But if you are focusing, you cannot, actually, there is some results that shows that you cannot define a global KMS, a global Gibbs system. Because of the integrability condition, your Hamiltonian is the maybe negative and positive part. So the integrability condition fails. However, if you define it on a shell of the mass, L2, then you are able to define a sort of get-up Gibbs measures. And this is enough to build, again, a global solution. Whenever you are able to define a global solution for UV, you are able to get global solutions as well for the initial value. Okay, so this is we extended with the work with Andrew and Vedran, where we formulated a sort of local KMS condition. It's only local KMS condition, not a global KMS condition. And thanks to the local KMS condition, it gives us that also we can define global solutions for focusing R3 and NLS equations on the torus and for these dimensions. Okay, so maybe so few motivations for the future is that we also interested on integrable systems, also derivation of KMS boundary condition from quantum KMS conditions. We have done this on finite dimensions. We would like to extend it on infinite dimensions. And one of the motivations, the long-term motivations, is to prove either that there are examples to classify sort of the main nonlinear equation, which one are ergodic, which one is not. Okay, thank you very much.
So, are there any questions?
If you want to establish global existence for nonlinear PDE, then there's in the presence of conservation laws, there is a very physically intuitive way of proceeding, that the norm that is conserved is actually equivalent to the Sobolev norm.
Yep.
Okay, you know that. My question is, where is this in? Is it reflected somewhere in your framework, and if so, where?
Yeah. Indeed, this is a very important point in the sense that these type of equation, for example, dispersive equations, they have energy conservation, they have momentum conservation, you have mass conservation, L2 conservations. So these quantities are conserved. Nevertheless, this allows you, for example, to use these conservation laws at the same Sobolev level. So L2, it will be L2 space, energy would be H1. So that allows you to build the corresponding local or global well-posedness theories on the corresponding Sobolev spaces. But if you are interested on defining a flow on low regularity data, then you are beyond these things. So no one of these conservation laws holds actually for this data. So the last actually Gibson themselves is the last conservation law. Doesn't look like a conservation law, but this invariance of the managers is in some sense a conservation. That you are this is what is really used to build the global solutions in some sense.
Any other question? Well, there are the well-known examples of nonlinear focusing, nonlinear Schrödinger equations where the solutions blow up.
Yeah.
Now, in this framework, what fails there?
Indeed, but this is maybe hidden on the data that are negligible. So we don't see blow up because in the end we say that almost sure data have global solutions.
Oh,
But
okay.
maybe some few exceptional data have problems and have blow-ups and have
Okay.
non-uniques and so on. So everything is hidden by measure theoretical techniques on a set that is negligible for the measure. So the measure will never see these things.
So
So weird things could happen for this data.
So they fit into a framework, but they are in the measure zero set where you cannot give an answer. Right?
Yeah.
Any other question? Well, otherwise, thank you.
Thank you very much.